13.7 Differential Equations. So we'll go over this section to discuss general and particular solutions of differential equations. So the only thing new really for this section is setting up the integrals, and then we evaluate the integrals like we've been doing so far. So the general solution of dy dx equals f of x. So the general solution of our differential equation dy dx equals f of x is y equals the integral of f of x dx. Let's look at an example. Example 1. Find the general solutions for the given differential equations. Let's look at part A first. So we want to break the differentials up. So I'm going to multiply both sides by dx. So I get y equals 4 minus 9x squared dx. And I want to make sure that I have the same variables collected on separate sides. So over here on the right hand side I only have terms involving x. 4 doesn't have anything, but I'm going to keep it with the side. And then over on this side I have my y's, or my dy. And once I have that, then I'm going to integrate both sides. So I put the integral in front of them. Over here I'm integrating with respect to y. Over here I'm integrating with respect to x. So then I'm going to go ahead and actually integrate. Over here I get y, and over here I use the power rule and I get 4x minus 3x cubed plus c. I only have to write c, my constant of integration, once on one side. And then I'm done. If I can, I try to solve it for y and get y by itself. Part B. Same thing over here. I want to separate the differentials. So I'm going to multiply both sides of the equation by dx. So this is what I get. Notice here I have just x terms, or terms involving x, and dx. And over here I have dy by itself. I'm going to integrate both these sides, so I write the integral sign in front of both of them. Over here I'm integrating with respect to y. Over here I'm integrating with respect to x. So this is what I get after I integrate, and same thing for like before, I only have to write my constant of integration, my c, one time on one side. I'm putting it on the right hand side because I like to get y by itself when I can. Separation of variables. Alright, so sometimes you need to rewrite the differential equation to get all terms involving y, including dy, on one side of the equation, and all terms involving x, including dx, on the other side of the equation. Such differential equations are said to be separable, since the variables x and y can be separated. Alright, so these are a little bit more complicated than example 1. So example 2, find the general solutions for the given differential equations. So let's look at part A first. I'm going to subtract both sides by 3x squared. So this is what I get. And then I'm going to divide both sides by negative 2. Or you can think of it this way, as multiplying both sides by 1 over negative 2. Then I'm going to distribute the 1 over negative 2 through on the right hand side. So distribute that through, and this is what I get. Negative 4 plus 3 halves x squared. Now I'm going to multiply both sides by dx. So this is what I get. So I have my x terms and my dx on one side and my dy on the other side. So I'm going to integrate both those sides. So I put the integral sign in front of both of those. And then when I integrate, this is what I get. So on the left hand side, integral dy is equal to y. And over here I'm using the power rule to find the antiderivative, plus c, my constant. Part B. I'm going to multiply both sides by dx. Now over here I have a y. This variable doesn't go with my x's. I need to get y on the other side, so it's with dy. So I'm going to divide both sides of the equation by y. So now I have my y's and my dy on one side and my x's and dx on the other side. So I'm ready to integrate, so I'll put the integral signs in front of both of those. Then when I actually integrate, on the left hand side I get natural log of y, and on the right hand side I get 1/3 x cubed plus c, my constant of integration. Whenever I can, I like to try to get y by itself. So I'm going to see if I can solve this for y. And what I do is I make both sides of the equation exponents to base e. I'm using stuff from chapter 4 here. So the left-hand side, this simplifies to just y. And the right-hand side, I'm going to use my rules for exponents to write this as e to the 1/3 x cubed times e raised to the c power. Now e raised to the c is just a constant here, which means that e to the c is just a constant. So instead of keeping it this way, I'm going to write it as a different constant, m. So m is equal to e to the c power. And then I'm done. I've solved for y. Particular solution. So a particular solution of a differential equation is when you know the specific value of c. So you will be given some initial conditions, some more information, so that you're able to determine the value of c. A differential equation together with an initial condition is called an initial value problem. And we kind of already did some of these back in 13.1 at the end of that section. So for example 3, we want to find the particular solution for the given equation. Okay, so I multiply both sides of this equation by dx. So I've got all my x terms on one side and the dx there, and then my dy by itself on the other side. So I can integrate both sides, so I write the integral sign in front of both sides, and then I just integrate. So dy, the integral of dy becomes y, and over here I use the power rule on each of these terms. So I get 2x to the fourth minus x cubed plus x squared plus c, my constant. And then this information, I'm going to use this to determine what c should be. So I'm going to plug 4 in for y and 0 in for x. So when I do that, I can solve for c. I get that c equals 4. So the particular solution to my differential equation is y equals 2x to the fourth minus x cubed plus x squared plus 4. And then we're done with this section.